So let's start off our review session today by talking about the exam itself. Um, the prep guide here says spring of 22, but the format of the exam is exactly the same. The only real difference here is that there is a slight nomenclature change because, when I changed textbooks, they changed from calling them chapters to calling them modules. So really, that's the only difference there. So the format of the exam itself, there are 22 questions on the exam for Wednesday. 16 of them are multiple choice. The other 6 are short answer, mostly calculation kinds of questions. In total, this is an 86-point exam, but you'll only be graded out of 78. So you actually have the opportunity, again, depending upon your viewpoint, you can either skip a question or you can think of having a kind of a built-in bonus here that'll allow you to make some mistakes and not get penalized for it. In terms of coverage, there are going to be some questions related to nomenclature. I remember, even though we did that in module 2, remember I held that off of the first exam because I wanted to give you more time to get ready for those proficiencies. Now that those proficiencies have come, that is a style of question that I can ask you. And I will ask you a little bit about on the exam on Wednesday. So you need to know how to name ionic compounds. You need to know how to name covalent compounds. You need to know how to name acids. Best practices for those are the proficiencies related to those areas. So if you haven't passed those proficiencies, use the next 2 days and take those extra attempts. Can't hurt anything to knock out a proficiency while you're studying for an exam. Out of module 4, which is about 1/4 of the exam, we're talking about balancing equations. We're talking about stoichiometry and limiting reactants. We're talking about yield. So being familiar with those 3 concepts, know how to do those calculations, know how to really do any kind of unit conversion kind of problem that is related to stoichiometry. And that includes titrations and solution stoichiometry out of module 5, which is chapter 8 here. Out of module 5, you need to know the basic parts of concentration. So you need to know what molarity and mass percent are. There won't be any questions on here about parts per million or parts per billion, so you don't have to worry about that. You also don't have to worry about being able to convert between molarity and mass percent. That's not something that we talked about either. You do need to know, and you saw this in the module 5 quiz, you need to know about electrolytes. Can I look at a compound and determine what kind of an electrolyte is it? Can I put it into one of those 6 bins like we did in the solubility rules proficiency? You also need to be able to identify acids and bases by formula as well as by behavior. And I think that was one of the biggest stumbling blocks on the module 5 quiz. A lot of you were trying to identify the acid and base based on formula, but you were looking at a chemical reaction. You had to look at how it was behaving in that reaction, not just looking at its formula. And so there were a couple of places where you looked at an OH and said, oh, that's got to be a base, and not realize that that OH is actually giving away its H, and so it's actually acting like an acid. The big concepts out of module 5, net ionic equations, because they kind of build off of all those previous concepts of electrolytes and identification. Redox reactions, being able to know how to assign oxidation numbers to things and identify oxidizing agents and reducing agents. and being able to carry out stoichiometry in solutions, using molarity as that bridge to moles. Or if I have two solutions, using the titration equation to figure out the molarity or the concentration or the volume of whatever is missing. So that is the write-up here. This will be your equation sheet. Very similar to the equation sheets you've been using for all of the quizzes for the first exam. And I will be supplying you with a periodic table as well, although that periodic table will not be bundled into the exam this time. Something about the page count. But what I'll do is I'll provide you periodic tables, and hopefully those ones will be a little bit clearer. I know the last one's kind of printed out a little bit blurry. And so they're readable, but they could have been better. And that was a print processing kind of issue that we ran into there. All right, any questions about exam format? Okay, so what we'll do now, I will open this up to you. You've got about 40 minutes. Ask whatever questions that you want to ask. If you want to bring up stuff from the practice test, we can go ahead and look at that kind of stuff. If you have broader general questions that you want to cover, other concepts that you want to explore further, now's the time to ask. Go ahead, Tess. 8. All right, number 8 asks, which of the following statements is true regarding electrolytes and non-electrolytes? Okay, so we have to explore, all of these statements have some kernel of truth to them. It's a matter of figuring out which ones actually are fully true as opposed to just partially true. So we didn't talk about molten compounds, but we could rationalize that if I had a molten compound, that molten compound, because now the solid is in the liquid phase, I have ions that are able to move now. They should be good conductors of electricity. And since conductivity is all about whether or not a charge can move through that area because there are other charges present, if I liquefy that solid, those ions are now free to move, which means the electric charge is now free to move. So we wouldn't get weak conductivity. We would actually get strong conductivity. It would be strong. It would be strong because we don't have just a few ions present. It's all ions present in a molten ionic compound. So they are electrolytes, but they're in fact strong electrolytes, not weak. Graphite is a conductor of electricity. Just because you are a conductor of electricity, does that mean that you are actually a good electrolyte, though? Has to be able to dissolve in water. That's the whole point. Does graphite dissolve in water? If I swish my pencil around in a cup of water, is the pencil lead going to dissolve? Not a chance. So there's a difference there. Conductivity doesn't necessarily mean electrolyte. Same thing. Metal is a really good conductor, but metal doesn't dissolve in water. It might dissolve in acid, but it doesn't dissolve in water. So A and B both have issues. All molecular compounds dissolved in water behave as non-electrolytes. Well, that sounds pretty good. Sugar doesn't conduct electricity. Alcohols don't conduct electricity. What we're forgetting is that acids are molecular compounds. Hydrochloric acid is a molecular compound, HCl. When we dissolve that in water, it breaks apart. So it's not a non-conductor, it's actually a conductor. So acids would be the exception to this rule. Related to that, letter E, all acids ionize completely when they dissolve in water. We know that's not true. That's the definition of a strong acid. Not every acid is a strong acid. So we've eliminated every option but D. Why is D correct? Well, we're talking about ionic compounds that dissolve in water, contain mobile ions, and are strong electrolytes. If an ionic compound does dissolve, remember, ionic compounds only have two categories. There's the soluble salt and the insoluble salt. The soluble salt, in an ionic equation, we always split it apart. Why do we always split it apart? Because those ions separate from each other. And in water, separated ions are mobile. They're going to move. And that's what allows electrical conductivity to exist. So strong electrolytes would result from those. So D would be our correct answer. Go ahead, Jesse.
But the question is, how can the weight of AL3 that contains 2.61 grams of it? Okay, so you take the 2.61 grams of it, and you like subtract that from the grams of compound.
Okay, so if you're given a problem like that, that's kind of like a mass percent problem. So just give me the parameters again there, Jesse. We'll go through this real quick.
In parentheses, that contains 2.61 grams of it.
Oh, it contains 2. Okay, and so we want to know how many grams of aluminum permanganate contain 2.61 grams of manganese, right? Okay. Now they give us the molar mass of the. Okay, but they give us the molar mass of the aluminum permanganate, right?
No.
Okay.
You have to figure out.
Okay. Okay, so this is a concept that we've been looking at since module 2. This is looking at an element inside of a compound. So 2.61 grams of manganese, I can turn that quickly into moles by taking the molar mass. Molar mass of manganese, 54.94 grams in every mole. So my grams of manganese cancel. I'm now looking at moles. From the chemical formula, I can look at this and say, okay, every 1 aluminum permanganate has 3 manganese. And so going back to this particular quiz question, this is where a lot of you ran into problems, was not recognizing the relationship between the element and the compound. Most of you did this first step. A lot of you did the last step. The step in the middle was the thing that was the most commonly missing. So the last step here would have been to turn the 1 mole of aluminum permanganate into grams of aluminum permanganate. And for that, we'd have to calculate that molar mass. So aluminum, 26.98, 3 manganese, 54.94, 12 oxygen, 383.80 ends up being our molar mass. And so if I do out the whole calculation here, 2.61 times 383.8 divided by 54.94 divided by 3, the 3 significant figures, it'd be 6.08 grams of aluminum permanganate. So this is kind of the traditional approach, let's say, to this kind of problem. Now, the other kind of approach that you could take with this is if you recognize this as a mass percentage, I'm taking a part of a whole, I could apply that same kind of thing proportionally. And so if I was looking at this from a different lens, I could look at this and go, okay, 2.61 grams of manganese over X is equal to how many grams of manganese are in aluminum permanganate? Well, there's 3 manganese. So 3 times 54.94 is 164.82. And the molar mass we just calculated, 383.80 grams of the whole thing. I could solve this proportional, cross multiply, and then divide. So 2.61 times 383.8 is 1001.718 is equal to 164.82 times X. So if I divide each side by 164.82, rounding again to 3 significant figures because that's our limiter here, I'd get the same 6.08 grams. So 2 approaches to the same problem. This one focuses on the relationship, knowing that this is a mass percent at its very heart. And so if I figure out the mass percent of manganese in the aluminum permanganate, I could figure out the amount of permanganate or the amount of products that contain that amount of manganese. The percentages would be equal to each other. Or I could solve it more stoichiometrically inclined with the blue equation there, where I just go step by step through it, kind of like we've been teaching you this whole time with dimensional analysis. Both ways work. One way probably works better for some of you than others. And so that's just a matter of preference. All right, any questions? All right. Other ideas that we want to bring up? Good, Tess. Okay. Okay, short answer number 3. Okay. So this is actually very similar to how the equations in your oxidation numbers proficiency are going to look on Friday. So like I said, this is a crossover concept. You know, as you're studying for this, you're also studying for Friday. So what we need to do is we need to determine, is this an oxidation reaction? And the way that we do that is we have to assign oxidation numbers to everything and see what changes. So first one, I've got carbon monoxide. Well, I know that carbon's -2. And since this is a positive, or this is a neutral compound, that means that the carbon has to be +2 to compensate, because it has to even out. For the hypochlorite, I know that the oxygen is -2. The chlorine here has to be +1, because remember, I've got a -1 charge overall. The two numbers have to add together to give me that charge. So if the target is -1 and I already have -2, +1 must be the thing that I'm missing to turn that -2 into a -1. In the products, I've got the carbonate ion. Again, I know oxygen's -2. I could set up a little equation for myself here. Carbon and 3 oxygens equals -2. Oxygen's -2. So carbon and -6 equal -2. Carbon must be +4. So right away, just off of this, I can answer that first analysis question. It is definitely redox. And I know it's redox because the oxidation numbers are changing. That's my telltale sign. If the oxidation numbers don't change, it's not redox, it's something else. But if the oxidation numbers do change, then it has to be redox. All right, the oxygen in the carbonate ion, we've already determined it's -2. That part did not change. For the chlorine, I've only got chlorine here. Chlorine by itself, the molecule is neutral. The chlorine atoms must be neutral as well. So what I can see here is that the carbon went from +2 to +4. So it's getting more positive, less negative. To become less negative, I have to lose electrons. The loss of electrons is oxidation. So I know that the carbon was oxidized, which means that the chlorine must have been reduced. And we can prove that. We went from +1 to 0. This got more negative, less positive. More negative means more electrons. Gain of electrons is reduction. So that's what we're seeing there. Now, the question doesn't ask us that, but it's important to identify those because that's how we identify the oxidizing agent and the reducing agent. So I can see that the carbon was oxidized, which means that the other thing must have oxidized it. The other thing in this case is the hypochlorite ion, ClO negative. I can see that the chlorine was reduced. What reduced it? The other reactant. So that would have been carbon monoxide. And so the thing to remember with redox reactions, first of all, we have to recognize that there's a change. Second thing that we have to recognize is that the reactants are going to be the things that are doing the oxidizing and doing the reducing. The elements get oxidized and reduced, but the reactants do the action. And so oxidizing agents and reducing agents will always be reactants. They'll always come from the reactant side of the equation. But it will also, and this is important, it'll also be the full reactant, not just the element that gets changed. All right, more questions? Any questions with this one?
This popped up from module 5, please. It says identify the acid and the base of the following reaction. I thought that looking at the equation itself could tell you whether it's acid or base. I thought that acid started with H and base with N.
If we are just looking at the chemical formula and nothing else, then that is a proper way of identifying acids and bases, is hydrogen in the front for acids, hydroxide at the back for bases. Problem with that approach is that if we are looking at chemical reactions, we have to look at the action of the substance, not just its formula. So that's going from what we've been talking about, the Arrhenius definitions, where I can just look at the formula and make a determination, to the Bronsted-Lowry definition that we talked about in module 5 that looked specifically at the action. And so when we're looking at the action, we have to look at where is that H plus going. And so if I'm looking at an H plus substance, I need to recognize, so let's just take a look at this one, for example. This equation right here. Yes, we can identify the H2SO3 as an acid. We can identify the KOH as a base based off of their formulas because they fall into the most strict definitions of acid and base. However, we can also identify them based upon that same kind of action when we recognize that the H's in the H2SO3 have gone away to turn the H2SO3 into just SO3. And where did those H's go? Well, they went to the OH to make water. So from an action standpoint, acids give away hydrogen ions and bases take in hydrogen ions. And so where we got a number of you was if we had a reaction like this, and asked you to identify the acid and the base, based upon those Arrhenius definitions, you'd have looked at this and said, oh, well, I've got a hydroxide and a hydrogen. The element or the compound on the left is a base. The compound on the right is an acid. But if we look at the action here shows, no, wait a second. this hydrogen moved from here to there. The movement of that hydrogen makes this an acid. The acceptance of this hydrogen by the bicarbonate ion makes this a base.
So even if like one of the reactants is H2O, it could be an acid.
Yeah, water actually is something called amphiprotic. It can act as acid or base depending upon the situation. So what you have to watch out for is if you're looking at a reaction that has water in it, look at the products. Do you see hydroxide on the other side? Or do you see hydronium, H3O plus? That tells you what the water did. If it took on that H plus and become H3O, then we know that the water was a base because it took in that hydrogen. If we see hydroxide on the other side, we know that the water acted as an acid because the difference between water and hydroxide is the loss of that H plus. So this particular concept of acids and bases, we kind of set you up here. That compound there, the CH3COOH, that is acetic acid. That is acetic acid in its molecular kind of structure. That's how acetic acid bonds to itself. You've got one carbon with 3 hydrogens around it, bonded to another carbon with an oxygen and an OH group on it as well. In organic chemistry, that is often how acids will appear, is with this carbon, oxygen, OH kind of configuration at the end. But it's the action that tells you whether it's an acid or a base. So especially if you see acids and bases in reactions, you have to look at the action, not just the formula. If I just give you the formula and say, what is this? Then yeah, you can use those Arrhenius type definitions. Oh, it's got an H, it's an acid. Oh, it's got an OH, it's a base. But if I'm putting that substance in a reaction, I've got to do more than that. Because I have to look at how it's actually behaving, not just what it is. Because some substances can do both. All right, other questions? More questions? No. In chemical reactions, it's all about electrons. It's always about electrons. So a reduction would be a decrease in oxidation number, yes. Now, remember, if we are adding or losing protons, that's a nuclear reaction. That's a reaction that is beyond just simple chemistry. We don't change chemical identities without a big dose of radioactivity going along with it. And since we haven't talked about that, and we're not going to talk about that, at least not in this class, you can throw out pretty much any answer that involves gaining and losing protons, because that's not a reaction that happens easily or often. So for a question like number 15, how do I know which species is oxidized? I have to assign oxidation numbers. So I would have to look at this and say, okay, this copper is a 0 because it is completely by itself. For the iron sulfate here, I've got the iron ion, iron 2+, and the sulfate ion.
I was talking about the question 3.
Okay, so going back to the one we looked at a minute ago.
Yeah, but
Okay, so again, it comes down to the oxidation numbers. Remember, we looked at this and said this is +2, this is +4, this is +1, this is 0. Anytime we see changes in oxidation number, that tells us that it's redox. Going back to the problem that I was just looking at, number 15 in the multiple choice, we're told that it's redox. And here's a little trick that can really help you. If I see in a chemical reaction common ions, so those have their sulfate on both sides of this reaction, that tells you right away nothing in that cluster, in that ion changed. It was sulfate before, it's sulfate after. I don't even need to bother assigning oxidation numbers because I know they didn't change. Whatever the sulfur was in sulfate in the reactant, it's going to be exactly the same in sulfate in the product because the ion itself didn't change either. So right away, I can eliminate those two options. The sulfur and oxygen didn't appear anywhere else, and we know that it didn't change. So now it's just down to copper, iron, or is it not redox? And we can eliminate this one because if I recognize that this is a single replacement reaction, all single replacement reactions are redox. Of the 5 types of equations I talked to you about, the only one that is definitively not redox is double replacement. If I have any of the other 4 kinds, there's a redox element to each of them. So this answer really only comes up if I'm looking at a double replacement reaction. If I don't have double replacement, I can eliminate E as an option as well. Now I just need to look at what happened. Copper initially is 0. Now it goes to +2. Iron was +2. Now it goes to 0. Well, which way is oxidation? Oxidation is the loss of electrons. If I lose electrons, I'm going to get more positive. Copper is the one that got more positive. So copper would be the correct answer there. All right, we've got about 5 minutes left. Probably time for a couple of questions. Okay, sure. Okay. 7, we need to recognize 7 as a dilution problem. We're starting with a high concentration of hydrochloric acid. We are preparing a lower concentration of that same acid. So right out of the gate, I need to recognize this for what it is. It is a dilution kind of equation. As a dilution equation, we're going to use the dilution equation. M1V1 is equal to M2V2. Now, what I choose as M1V1 and M2V2 really doesn't matter so long as I'm talking about the same thing on the same side of the equation. So I've got 3 molar HCl and 250 milliliters of it on the one side. I've got 12.1 molar HCl and unknown quantity on the other. Divide each side by 12.1 molar. Molar cancels out on the number side. Everything is 6 for V2 on the other side. 3 times 250 divided by 12.1 will give us 61.98, which rounded to 3 significant figures is 62.0 milliliters. So that would be D. Okay.
I just want to make sure.
Number 6 here. Okay. Okay, this problem here, this is not a question that you have to worry about. I'm not going to ask you to interconvert mass percent and molarity. That is something that we used to ask you to do. We're not asking you to do it this time because the book that we're using doesn't emphasize that calculation. If you did, you know, you'd basically use a stoichiometry kind of approach to do it, but we're not going to worry about that here. So if you're interested, it is in the key how to do that one. But again, it's not super important that you know how to do it. Like I said, if you're interested, it is there, but you are not going to get a question like that on Wednesday. All right. Any last quick hitter kind of questions? Okay. No stoplight question for the end of today. Just want to make sure that if you have not signed in, make sure that you did sign in so that you get marked as present for today. Otherwise, as you're getting ready, you know, take this kind of stuff into consideration. What do I know how to do? What don't I know how to do? And make sure that you are actually practicing these problems and not just reviewing these problems. There's a big difference between looking at something and doing something. If you just look at the examples and if you just look at your notes, you're going to be looking for trouble because you're not going to actually be able to do what you need to do. So make sure that you're practicing by actually run through practice problems, run through some of those extra kinds of questions. If you have anything that you need or want, feel free to reach out to me over the next couple of days. I'll see you on Wednesday.